study crystal field theory in detail, today we are going to discuss number of unpaired electrons, that is high spin and low spin tetrahedral complexes, calculation of crystal field stabilization energy for a tetrahedral complex, octahedral versus tetrahedral complexes, factors influencing the magnitude of crystal field stabilization energy and limitations of crystal field theory. By now, you know that crystal field theory provides a simple model for d orbital splitting, which works for several oxidation states and geometries and allows prediction of properties such as structures, colors, magnetism, etc. In last lecture, we understood these by discussing calculation of crystal field stabilization energy for octahedral complexes, splitting of 5d orbitals in stronger and weaker tetrahedral field, distribution of d electrons in T2g and Eg orbitals in tetrahedral complexes. Today, first we are going to discuss number of unpaired electrons, that is high spin and low spin tetrahedral complexes. As we have discussed in earlier lecture, for tetrahedral complexes, you know that weak field complexes of D3, D4, D5 and D6 ions have greater number of unpaired electrons than those of strong field complexes and are thus with higher value of regular spin, which you can denote by capital S. It is for this reason that the weak field and strong field complexes are also called spin free or high spin and spin paired or low spin complexes respectively. High spin complexes are abbreviated as HS and low spin complexes are abbreviated as LS. The number of unpaired electrons in the cases, namely D1, D2, D7, D8, D9 and D10 is the same in both the fields, and it is due to this reason that for these configurations the question of formation of high spin and low spin complexes does not arise. The question does arise for the systems D3, D4, D5 and D6 only. The paramagnetism of high spin complexes is larger than that of low spin complexes because high spin complexes have more unpaired electrons, that is larger value of capital S than the low spin complexes. The distribution of d electrons in the T2g and Eg levels in a central ion surrounded by tetrahedral ligands exerting weaker and stronger fields is shown in this table. Here you can see for D1 and D2 configuration, the distribution of electrons in Eg and T2g levels is same for high spin complexes as well as for low spin complexes. Therefore, number of unpaired electrons for both is also similar. But in case of D3, D4, D5 and D6, number of unpaired electrons for high spin complexes and low spin complexes is not same. For example, for D4 system, for high spin complexes, the electronic configuration will be Eg2, T2g2 with 4 unpaired electrons, and for D4 low spin complexes, the electronic configuration will be Eg4, T2g0 with 0 unpaired electrons. For D7, D8, D9 and D10 systems, again the number of unpaired electrons for weak field, that is high spin complexes, and for strong field, that is low spin complexes, is similar because electronic configurations in both the cases are similar. In principle, both high spin and low spin configurations are conceivable for D3 to D6 for tetrahedral complexes. But with extremely rare exceptions, only high spin configurations are observed. crystal field energy for tetrahedral complexes, that is delta T, is very less than pairing energy in ordinary complexes. So, high spin is favored. Let us calculate the crystal field stabilization energy for a tetrahedral cobalt 2 complex. You know that cobalt 2 is a D7 ion. The electronic configuration of the free ion and the tetrahedral complex are shown here. Here you can see the electronic configuration of cobalt 2 plus in free ion, and here the electronic configuration of cobalt 2 plus in tetrahedral field. You can see there are 4 electrons in lower energy level, which is Eg, and 3 electrons in upper energy level, which is T2G. Now, for the calculation of crystal field stabilization energy, you have to calculate 4 electrons with minus 3 by 5 delta T and 3 electrons with plus 2 by 5 delta T. Ultimately, you will get crystal field stabilization energy equal to minus 1.2 delta T. Now, let us discuss octahedral versus tetrahedral complexes. The crystal field stabilization energy is usually greater for octahedral than tetrahedral complexes. In fact, delta T is approximately equal to 4 by 9 delta O. We can calculate the difference in stabilization energy between octahedral and tetrahedral geometries by putting everything in terms of delta O. For example, for a D3 octahedral configuration, the crystal field stabilization energy is minus 1.2 delta O. For a D3 tetrahedral configuration, assuming high spin complex, the crystal field stabilization energy is equal to minus 0.8 delta T. Remember that because delta T is less than half the size of delta O, tetrahedral complexes are often high spin. We can now put this in terms of delta O. We can make this comparison because we are considering the same metal ion and the same ligand. All that's changing is the geometry. So, for tetrahedral D3, assuming high spin complex, crystal field stabilization energy is equal to minus 0.8 into 4 by 9 delta O, which is equal to minus 0.355 delta O. And the difference in crystal field stabilization energy between the two geometries will be minus 0.845 delta O. If we do the similar calculation for the other configurations, we can construct a table of delta O and delta T. We can make this comparison considering the same metal ion and the same ligand. Here you can see the comparison of crystal field stabilization energies for high spin and low spin octahedral complexes and high spin tetrahedral complexes. For example, if we take a D2 configuration, then crystal field stabilization energy for high spin octahedral will be equal to minus 0.8 delta O. For low spin octahedral, this will also be equal to minus 0.8 delta O, but for tetrahedral this will be equal to minus 1.2 delta T. Similarly, if we take an example of D9 configuration for high spin octahedral, you will get minus 0.6 delta O. For low spin octahedral also it is minus 0.6 delta O, but for tetrahedral it is minus 0.4 delta T. From these values, you can calculate the difference between crystal field stabilization energies for octahedral and tetrahedral complexes. As crystal field stabilization energy is very important factor in explaining crystal field theory, so let us discuss factors influencing the magnitude of crystal field stabilization energy. Some of the important factors are nature of metal cation, stronger and weaker ligands and spectrochemical series, and geometry of the complex. First, we are discussing the nature of metal cation. If we take different charges on the cation of the same metal, then the cations from atoms of the same transition series and having the same oxidation state have almost the same value of delta O, but the cation with a higher oxidation state has a larger value of delta O than that with lower oxidation state. For example, you can see the value of crystal field stabilization energy is greater for Fe3 plus than for Fe2 plus. Similarly, the value of CFSE is greater for cobalt 3 plus than for cobalt 2 plus complexes. This effect is probably due to the fact that the central ion with higher oxidation state, that is with higher charge, will polarize the ligands more effectively, and thus the ligands would approach such a cation more closely than they can do the cation of lower oxidation state, resulting in larger splitting. Two different cations having the same number of d electrons and the same geometry of the complex but with different charge can also be compared. The cation with a higher oxidation state has a larger value of delta O than that with a lower oxidation state. For example, the behavior towards same ligand of vanadium 2 and chromium 3, which are both D3 ions, can be compared. You can see the crystal field stabilization energy for vanadium 2 is less than the crystal field stabilization energy for chromium 3, while both are D3 ions. This fact can be explained in terms of charge on the cation. The chromium 3 plus ion, which has greater positive charge than vanadium 2 plus ion, exerts a greater attraction for water molecules which acts as ligands here. Hence, the water molecules approach the chromium 3 plus ion more closely than they approach the vanadium 2 plus ion, and so exert a stronger crystal field effect on the d electrons of chromium 3 plus ions. In case of complexes having the cations with the same charges but with different number of d electrons, in the central metal cation, the magnitude of delta O decreases with the increase of the number of d electrons. Example, you can see the delta O value is greater for cobalt 2 than for nickel 2. Cobalt 2 is a 3d7 system and nickel 2 is 3d8 system. Both the metals have same charges. From the combination of 3 points discussed here, we can conclude that for the complexes having the same geometry and the same ligands but having different number of d electrons, the magnitude of delta O decreases with the increase of the number of d electrons in the central metal cation. In case of complexes having the same number of d electrons, the magnitude of delta O increases with the increase of the charge, that is oxidation state on the central metal cation. Delta O increases about 30% to 50% from 3D to 4D and by about the same amount again from 4D to 5D complexes. For example, you can see here crystal field stabilization energy is increasing from 3D to 4D series and from 4D to 5D series. Presumably, the 4D and 5D valence orbitals of the central ion are better than the 3D orbitals in sigma bonding with the ligands. The next factor which influences the magnitude of crystal field stabilization energy is stronger and weaker ligands and spectrochemical series. The magnitude of delta O varies from stronger to weaker ligands. Stronger ligands are those which exert a stronger field on the central metal ion and hence have higher splitting power, while the weaker ligands are those which have a weaker field on the central metal cation and consequently relatively lower splitting power. Thus, stronger ligands like Cn- give larger value of delta O and weaker ligands like F- yield a smaller value of delta O. This figure shows that not only delta O, which represents the energy difference between T2G and Eg sets of orbitals, is smaller in weaker field complex than in stronger field, but also that both the T2G and Eg set levels of the weaker field are correspondingly closer to the level of degenerate 5d orbitals of the metallic ion than are those of the stronger field. The common ligands can be arranged in the order of their increasing splitting power to cause the d orbitals splitting. This series is called spectrochemical series, which you can see here. You can see iodide is the weaker field ligand and Cn- Co are stronger field ligands. This series shows that the value of delta O increases from left to right in the spectrochemical series. The order of field strength of the common ligands is in fact independent of the nature of central metal ion and the geometry of the complex. In this example, you can see the delta O value for a lower field ligand F- is smaller, while the delta O value for a stronger field ligand, that is Cn- is larger. The increase in the value of delta O on proceeding from left to right in the spectrochemical series is quite evident from the values of delta O for some octahedral complexes given in this table. In this table, you can see the values of delta O increases for all the metal ions as the ligand changes from weak field to stronger field. Another very important factor which influences the magnitude of crystal field stabilization energy is geometry of the complex. We have already seen that with the change of the geometry of the complex, the value of crystal field stabilization energy also changes. It has already been seen that crystal field stabilization energy for square planar complexes is greater than the crystal field stabilization energy for octahedral complexes, which again is greater than the crystal field stabilization energy for tetrahedral complexes. To understand the factors influencing the magnitude of crystal field stabilization energy, let us exercise an example. Which complex of the given pairs has the larger value of crystal field stabilization energy? First pair is CO CN6 3- and CO NH36 3+. Since Cn- is a stronger ligand than NH3, therefore, crystal field stabilization energy for CO CN6 3- is greater than that for CO NH3 6 3+. Second example is CO H2O 6 3+ and RH H2O6 3+. RH is a member of 4T series, while CO is a member of 3D series. Thus, principal quantum number n for RH is greater than that for CO and consequently delta O for RH H2O6 3+ is greater. Next example is CO H2O6 2+ and CO H2O6 3+. The charge on CO in CO H2O6 3+ is higher than that on CO in CO H2O6 2+. Thus, delta O value for CO H2O6 3+ is higher. If we summarize the factors affecting crystal field stabilization energy, we can say that the magnitude of delta O depends on both the metal ion and the attaching ligands. When the geometry and the ligands are held constant, this splitting decreases in the order as Pt4 plus, Ir3 plus, RH3 plus, CO3 plus, Cr3 plus, Fe3 plus, Fe2 plus, CO2 plus, Ni2 plus, Mn2 plus. When the geometry and the metal are held constant, the splitting of the d orbitals increases in the order I minus, Br minus, NCS minus, Cl minus, F minus, OH minus, NH3, En, Cn minus, that is from weak field towards strong field. Delta O gets larger for increasing oxidation state. It increases down the group. Example, for IR, delta O is greater than RH, and for RH, delta O is greater than CO. With a given ligand and oxidation state, delta O varies irregularly across the first row transition metals. Most aqueous complexes are high spin because H2O is a weak field ligand. Almost all CO3 plus, that is D6 complexes are low spin, including CO H2O6 3 plus, except COF6 3 minus, which is a high spin complex. Note that the crystal field model does not explain the bonding in coordination complexes. It describes only behavior that can be attributed to electrons on the transition metal atom in the coordination complexes. Crystal field theory has some limitations also. Crystal field theory considers ligand as point charge or dipole only. Crystal field theory does not take into account the overlap of ligand and metal orbitals. It considers only the metal ion d orbitals and gives no consideration at all to other metal orbitals such as s, p and f orbitals and the ligand orbitals. Crystal field theory is unable to account satisfactorily for the relative strengths of the ligands. For example, it gives no explanation as to why H2O appears in the spectrochemical series as a stronger ligand than OH minus. According to crystal field theory, the bond between the metal and ligands is purely ionic. It gives no account of partly covalent nature of the metal ligand bonds. Thus, the effects directly dependent on the covalency cannot be explained by crystal field theory. With this, we come to the end of the lecture. Let us revise what we have learnt in this lecture. Number of unpaired electrons, that is high spin and low spin complexes. Calculation of crystal field stabilization energy for a tetrahedral complex. Octahedral versus tetrahedral complexes. Factors influencing the magnitude of crystal field stabilization energy and limitations of crystal field theory.